Hi and welcome. In this tutorial, we're going to be looking at how to set up a project in GenFEA and how to produce a model using the built-in features. So the most important thing to do is when you start up GenFEA, make sure that you've got the latest update. If it says new update available, I would encourage you to apply the update because as you can see in the What's New features, we fix bugs and we add new features as we go. So it's always important to check for the latest updates. To create a new project, simply click on the Create New Project button from the Welcome screen. You can also do it from the Application menu. Specify a name and specify a project location. We'll use Singapore for this example. And why is this important to specify a location? You're going to see later because the artificial intelligence is going to use that to understand what standards to use. Now you saw there, we are using Newton, millimeters, and tons as the units. You can of course change that. Now let's have a look at the input workbook. GenFEA is driven by a database, which is in the format of Excel spreadsheets. And you can see there on the screen, we're currently on the project info sheet, and we can change to the materials sheet. And when we do so, you'll also notice that the ribbon menu at the top keeps changing. So whenever we access any workspace, like the model, then the ribbon changes to the model. If we go back to the input workbook, then you'll see once we click inside of it, the context ribbon again in the top will change. So the ribbon changes to the applicable commands for the current workspace that you're in. Now we're going to add some materials. So I'm adding two materials here, as you can see on the screen, one for concrete and one for steel. And we're going to move to the sections sheet where we are going to add a couple of cross sections. So from the library, we'll add a universal column section. Then we'll add a universal beam section. And then we are going to add a circular hollow section. And finally, we'll add another section, the cold formed lip Z, which we're going to use for purlin. So we're going to be building a mixture of concrete and steel model here, a steel frame with some concrete shell elements to demonstrate how it's done in GenFEA. We'll also add a planner section here for the shell elements, and we'll just call this one shell 200, and that's going to be 200 millimeter planner thick shell section. Okay, so now that we've done that, again, you can see we're clicking inside of the sheets and the context ribbon is changing. This time we're adding design groups. So design groups are important. They're kind of layers that we use to allocate members to, so that when we get to the design stage, we can filter for those elements within those design groups and design for them. So we'll create columns, rafters, purlins. We're going to create one for bracing. And as you can see there, we're assigning different colors to the different groups. And finally, one for floors. That's our basic setup that has now been completed. So from here on, we're going to be using the 3D modeling components to start modeling. Now, of course, in GenFEA, you can manually enter values directly in the spreadsheet sheets to create your modeling environment. But if you use the modeling interface, the principle is that whatever the grid is currently set active to, and we've rotated the grid here in 3D space, becomes the active working plane. So you can see there from the grid context ribbon, we've rotated the grid around the x-axis 90 degrees, and now we can start modeling. So we've clicked on Add Frame, and now we are going to specify the intersections on the grid that we want to snap to. You'll notice as we are drawing, it's indicating to us that it's drawing, and we'll just switch off the grid auto size so that we can have a larger workspace to work with. Again, we're adding a next section here. And this time we're going to create the rafter, again snapping to those intersections. We use the tools on the model to select the elements, and then we are going to select mirror, and we'll create a mirror line to mirror those elements across to the other side. We see in the audit palette there's some errors appearing. That's okay, don't worry about those. We are still busy working on the model, so we expect some complete items to be present. Now we are going to create another column. So I select from the context ribbon the columns group and the appropriate section, and we repeat the process, and we're going to create an additional rafter. So from the intersection to the intersection across the other side. And that is our 2D frame in a 3D space. So in GenFEA, and we'll just reset the grid here so it's back to normal. In GenFEA, we always work in 3D, but we can snap to 2D planes using that grid. Now notice when we switch on the frame labels that we've got some elements that are not split at the intersecting nodes, as you can see there on the screen, which will obviously cause a problem when we run the analysis. The same applies to the columns there. So we're going to use the discretize elements, and that's from the right-click context menu, and switch on the member nodes labels again, and you can see now the model is automatically discretized. So GenFEA can do that for you. Right. So now that we've done that, let's select the rafters, and we are going to split the rafters into smaller segments so that we can easily apply our purlins to it. And you'll see we've used 50% there as the split value, and I'm going to repeat that. So I'm going to select the 4 rafters again, and then I'm going to use the split frames, and the value is 50%. So each time we're splitting those by 50%. Now, in the next step, I'm going to switch on the frame and node labels so we can see what's the start and ending node of each frame, because now we're going to split the last remaining rafter segments close to the top there by 80%. So we only want a 20% before we actually get to the ridge. So you'll see we'll type in 80%, we click on apply, and it's going to split that element so that we've got an 80-20 split. And we can do the same for the one on the opposite side. So we can see we're from nodes 9 and 15 there, and the start node is 15, end node is 9. That means if we split it 80%, it's going to go from 15 towards 9, 80%, and that's what we want to do. Okay, so now that we've completed that, we can select our bay or our frame. I'm just going to switch on the auto grid size again, and then we're going to use the copy tool. I'm going to specify 2 reference point as my distance and direction. You can see there it's 5 meters in the wide distance, and I'm just going to click apply as many times as I need to create the remaining portal frames. Now that that is done, we can go ahead and draw in our purlin. So you can either right click and select frame and set the properties from the context menu, or you can press F, or from the model space you can just select the draw frame tool. Now notice we don't have to draw in between the frames. We know that the software can automatically discretize, so we just draw from the start all the way through to the end, and then we'll let the software do the model discretization automatically afterwards. So we'll just draw in those remaining purlins there, and to keep creating these I'm just pressing the F key on the keyboard, so that's the shortcut for drawing frames. And we're almost through here, and also I'm making sure that I've switched off my grid snaps here so I don't accidentally snap to the wrong location. So the grid snaps are there at the bottom of the screen. You'll see there's a toolbar. And here we go, we're running the model discretization. And if we just quickly do a visual inspection of the frame element labels, we can see that that looks pretty good, and it's all been discretized as we intended for it to be. Now for the next step, we are going to quickly just save the model. Very important, don't forget to do this, because if something goes wrong, you don't want to lose all the work you've done. So we've saved it, and you can actually click on the file name there at the bottom of the screen in the status bar, and when you do that, it's going to take you straight to where the file is saved. You can see again there, GenFEA files are saved as Excel spreadsheet files, which is great. We're going to draw in the bracing elements now. So I'm going to make sure I select the correct elements from the menu, and then I'm going to start drawing them in, as you can see there on the screen. Okay, so I'll just speed this up very quickly, and we'll draw in those remaining bracing elements on both sides. And once that is completed, we can start drawing in the shell elements. So you can see there from the main ribbon at the top on the model tab, we've got shell elements, but we can also access it from the right-click context menu. We're going to select the correct group, the correct material, and the section is already pre-selected since there is only one. Now we're just going to draw these shells in sort of halfway into this model. Then after creating the first panel, we'll use the copy tool like before, specify 2 reference points, and hit the apply button until we've created the remaining panels to fill the space as you see on the screen. It's important to note that the shell names need to be unique. The program tries to manage that as much as possible, but you also need to verify that that is the case. Then we're going to create a selection box and right click on those supports and choose edit properties. So let me just do that properly. So I'll just highlight all of those nodes, right click on the node, choose edit properties, and we are going to check the boxes for translation XYZ and rotation XYZ and hit apply. And what that effectively does is it is going to create supports at that node position. So we can see in the input sheet for the 6 degrees of freedom, we say yes, which means that it is fixed in those 6 degrees of freedom. Translation XYZ, rotation XYZ. And we can then proceed to click on the mesh button, and this is going to apply a uniform or a global mesh parameters to all of the shell elements in the model. So the software is quite intelligent. It'll keep track of intersecting elements such as columns, support points, edges of beams, all of that, and it'll automatically discretize them for us, so we don't have to worry about it. Now we're going to apply load. So what we're doing here is we're right-clicking on any shell within a particular palette or panel, and we choose select all from group. Now, before I get into adding the loads, let's create some load cases. So we'll create a dead load case here. We'll just call it DL, and we'll check the box that says contain self-weight. We're going to do the same, repeat the step. This time LL, and we will uncheck the box that says contain self-weight because we'll use that for the live load imposed loads. All right, so we're going to right click on any mesh element there and say select all from group. And when we do that, we just give it a second. It's going to find all the mesh elements or quad elements within that panel. And we will go to the loads sheet and then click on add, and we're going to do an area load of 0.005. This is newtons per millimeter squared, so that's 5 kilonewtons per square meter. We do the next for this, the same for the next panel. Right click, select same from group, click anywhere in the sheet. On the add drop down, area load, just change the load case to LL and hit apply. It'll remember the previous settings from the previous step, and we can just do this again. So we'll just repeat this for the remaining 2 panels. Great, so once that is all set up and complete, we should be able to add a load combination. So let's go and add a load combination from the load combination sheet. For DL, we're going to use a factor of 1.2. For live load, we're going to use a factor of 1.5. And you'll see I just click on the plus button and then apply there to apply that. Now that everything is done, let's just quickly do an update of the model, because that's going to run the audit process in the background. And we'll just look at the audit palette there and make sure we've got no issues in the model. Everything seems fine. Otherwise, they would have been listed there and we can deal with them. So now that everything is good, let's go ahead and, I forgot something. Actually, let's just add some edge beams here on the right-hand side of our model. So I'm quickly going to draw those in. Give me a second. So I'm using the same procedure as before, drawing in an element and then using the copy tool to copy it across multiple times. Okay, great. Now, if we switch on the support symbols, we can see the supports have been added to the model, and we should be good to go for an analysis. Let's just save the model before we do that. So I'm going to right click, choose run analysis. We can also select it from the model ribbon there on the right. You can see there's a run all button. Now, once we've clicked on that, it's going to again parse the model, check for any possible errors, and it's going to send that to the analysis engine. Currently, we've got 3 load cases, 1 for dead load, 1 for live load, and then we have the combination, which is a load case in its own, but with some factorization applied to it, of course. So we'll give this a second to run through. And once this is all completed, we'll switch to our combination 1 load case there from the ribbon, and we'll just wait for the results to be read in, and we are ready for viewing the results. So we'll click on deflection there and see what that looks like. Now, you'll notice here that those bracing elements are taking a lot of stress, which is not supposed to do. So we're going to click to clear the results. And what we'll do here is just quickly look at how we can do model adjustments using the input workbook features. So I'm going to right click on one of those bracing elements and then choose select all from group. Then I'm going to right click again and choose edit properties. Give it a second, and then from the context ribbon, we're going to choose tension only, and we're going to set those end release 1 and 2 to pinned, and we're going to hit apply. Now that that's done, we're going to right click and we're going to choose run the analysis again. So we can just verify here from the input workbook. If we filter for all the bracing elements, we can see there that they are all now updated to pin and tension only members. Okay, so now that we've verified that, save the model again and let's go and run the analysis again. So this will just take a second. So we'll let that go until it's finished. It's going to take slightly longer this time because it's actually doing additional checks for whether members are tension or compression, and then based on that, it's going to decide what to do with them. Once this is finished, we'll switch to the combination load case again, or the combination. And once it's read in all the results, we can start outputting those visually in the screen. So I'm going to click on deflection, and we can see there we've got our deflected shape for the frame and the shell elements. And we've got a legend there on the left telling us that we've got 5.7 millimeters deflection in the red zones. We can also animate that. So there's an animate button that you can press, and then you can actually see the exaggeration of the model higher and lower. All right, we can also mix results in the model. So first, let's switch on some values. So if you want to display values on the model, you can do so. And of course, if we wanted to view different results like shear values, torsion, or moments, we can switch those on in the model also. They're fairly small in the other parts of this model. So yeah. And then also for the shell elements, we can switch on moments and forces and whatever information it is that you want to see, and those just presented by those check buttons at the top in the ribbon, as you can see that I'm pressing right now. Now, once you've done this, you can also plot results on framing elements. So if I right click on a beam element and I choose select chain, it's going to select all the connected elements that is aligned with the selected element. And if we then click on the plot button, we can start plotting values along that member like deflection, axial, shear, torsion, and moments. You'll notice that it displays all the elements in there with their values. So if we wanted to plot those, that is how we do it. Now, this is quite important because we're going to use that later again when we send it to some external programs such as MemDes. Now, we can also export this to various formats, which I'll speak about in another topic, but one of them is Procon. We can export to SAP 2000, and of course, XL, DWG, IFC, and various other formats that can be used for post-processing. We can also import CAD, which I'm going to show to you in the next module. We can import SAP 2000, and we can import Procon files and also spreadsheets generated from Dynamo. I hope you found this useful. Let us know, give GenFEA a try, and have a great day. Bye.